Another big difference between the SN1 and SN2 reaction is the stereochemistry. Because the SN2 is only one step, I know my stereochemistry. It has to go from the backside attack, and so I'm going to see 100% inversion all the time. It can only happen that way. But the SN1 reaction is two steps. Remember, there's a little cation intermediate here, and so there is a space for shenanigans. Here are some shenanigans. So here we go. This is a really nice SN1 substrate because I've got a leaving group that is both tertiary and next to a benzene ring. So it's pi stabilized. So this is going to be fast. This bromine, let's say we have this in water. This bromine leaves and I have this carbocation. So here we go. Remember that cations, like alkenes, are flat. This is sp2 hybridized, after all. So I'm flat at this carbon. My question is, where is my nucleophile going to come in? Is my nucleophile going to come in from the top, or is it going to come in from the bottom? Right? Seems like it should be able to do either. Right? If something is flat, I don't see any reason why something would have preference for attacking here or there. And so I think I'm going to get an equal amount of products from bottom attack and products from top attack. So if it's equally likely to attack from the top or the bottom, I will end up with a racemic mixture, because attack from the top is going to eventually, once it loses that extra acid proton, attack from the top is going to give me the S enantiomer, but attack from the bottom is going to give me the R enantiomer, right? And so if it's equally likely, then I'll end up with a racemic mixture. My observed rotation will be 0 because I will have an equal amount of both things. Here's another example. I just showed this as a possible SN1 substrate because I can stabilize the charge next to that lone pair. So now I have two stereocenters on this ring. Notice that in the intermediate, now this stereocenter is destroyed, but this one isn't, right? Again, I'm not doing any chemistry here, so why would it change? It wouldn't. When this thing reacts with water, it's going to lose an acid proton after that, so I'm going to make an alcohol. As I said before, I can imagine my nucleophile attacking from either above this thing or below it. And so, if this is flat, I'm going to get some mixture of these two things. But because my other stereocenter didn't change, I wouldn't say these are enantiomers, right? They're not mirror images. I changed one stereocenter but not both. So these are diastereomers of each other. Am I guaranteed to get a 50-50 mixture? Not really, right? So you could imagine, and I haven't seen the experiment, but you could imagine that maybe this methyl group blocks attack from its side, right? So water comes in and that methyl group is like, go away, right? So in that case, I guess you'd expect maybe a little bit more of the trans, but I'd be very surprised if you had 100% and 0%, right? This is not a stereo-specific reaction. It is not like the SN2 reaction where I can only get one thing, right? Even if it's able to select between the two because one is lower in energy or whatever, that's not the same as stereo-specific, I can only make this. Okay, so I will, in an SN1 reaction, I will see scrambling of the stereocenter, but only at the carbon the reaction is happening at. If there are stereocenters in other places in the molecule, those are not affected. Finally, let's talk about solvent. So a lot of times I said in the SN2 reaction the solvent isn't that big of a deal. Polar aprotic often works best. That's your DMSO, your DMF, your things that are polar but not so polar that they overstabilize your nucleophile. But other solvents are okay. Polar protic solvents are okay sometimes. It's pretty chill. SN1 is less chill. SN1 needs a polar protic solvent. It needs something like water, methanol, maybe ethanol. I think longer chain alcohols like propanol, butanol, whatever, those won't work. They're not polar enough. So this is pretty much your list of alcohols that'll work, up to ethanol. and maybe some carboxylic acids. This is acetic acid. Again, acetic acid is nice and small and polar, so that's a good one too. But this absolutely needs a polar protic solvent, of which there are not many. This is kind of your list. Usually that solvent is also the nucleophile, so we usually don't bring in another good nucleophile like cyanide or whatever. So almost all the time when you're doing an SN1 reaction, the solvent is also the nucleophile. We call that solvolysis. The only exceptions would be if you had like HBr or HCl or something like that. There you might see Br minus or Cl minus as the nucleophile. Why is a polar solvent so important for the SN1 reaction? Well, think about what we're doing. We're trying to turn something very nonpolar, my haloalkane, into something very polar, a cation, straight up carbocation. The transition state to get there, the barrier that I need to get across, is also quite a bit more polar than my starting material. It has to be, right? I almost have a full positive charge. So the idea is the more polar my solvent is, the more it's going to stabilize this high energy stuff without stabilizing my non-polar starting material, right? It wouldn't do me any good to drag both down. And if I only drug my starting material down, my barrier gets taller. That's worse, right? That's kind of what overly polar solvents do over here. But in SN1 reaction, my high energy stuff is so polar that a polar solvent will stabilize those things but not stabilize my non-polar starting material, so my barrier gets lower, right? So again, both this intermediate and the transition state, it needs a polar solvent to stabilize them. Something really, really polar. Again, it's a pretty short list. Water, methanol, ethanol, acetic acid, right? These are our polar solvents that we can do. And again, almost all the time, these are also going to be the nucleophiles in our reaction. The reason I covered the SN2 reaction first is that it is just better than the SN1 reaction in a lot of ways. And the main way it's better, in my opinion and in almost every organic chemist's opinion, is that I know what I'm going to get at the end. Nothing weird happens. I know exactly how the mechanism has to go. The SN1 reaction can get a little weird sometimes, and we can dig into why it's weird. So here's an example. Here is some molecule. I've got this tertiary bromide at the end, near the end of the chain. When I boil it in water, one of my products, among others, that I'm going to get is this alcohol. This is not a typo. I didn't make a mistake. The OH does not end up on the carbon that bore the leaving group. The OH is now over here. Why did it move? Well, first let's draw the intermediate, the cationic intermediate that would be formed first in the slow step of this SN1 reaction. So here is my cation. Again, it's tertiary. It's relatively easy for me to make it. What the problem is here is this is a really electron poor carbon. And just like before when I said that lone pairs can stabilize it or other atoms can stabilize it, that stabilization by other orbitals in the extreme can just lead to this thing leaning over and not only giving it a little bit of electrons, but giving it all of its electrons plus the hydrogen it is bound to. What just happened? What just happened is that this hydrogen plus its electrons leaned over and basically walked one atom over. So now, before I had a filled sigma orbital here and an empty p here. Now that hydrogen plus its electrons have moved over, now that bond is over here, and now I have an empty p orbital here. This is actually quite a bit more stable because not only is a tertiary like that, now I've got resonance with the ring. And that resonance is a pretty big deal. So technically this is reversible. This could go back and forth, but this is quite a bit lower in energy. This is called a hydride shift. So hydride is H minus, like sodium hydride. And in a way, it's H minus that's moving over, right? It's H plus its two electrons. And it moves over because of orbital overlap, can give it something that is quite a bit more stable. And so when this cation eventually finds water, that is going to be the product that's resulting. These rearrangements can get really complicated, and I'm not looking to take too deep of a dive in it. But what I want to get across is that the SN1 reaction has some problems that the SN2 reaction doesn't. Stereochemistry for the SN1 can give me 2 stereoisomers, where the SN1 only gives me 1. But also, this cation can rearrange. If a cation can rearrange to give a more stable cation by basically taking either a hydrogen or really any bond to anything, it could be a methyl or whatever. If some bond can move over one to give me a more stable cation, it'll do it. And then I'll have that product in addition to all the other products that I have. So another problem with these carbocation intermediates is that they can do hydride shifts because cations can rearrange to give me more stable cations. So I might not have you kind of predict what kind of products you would see from these rearrangements, but given the rearrangements, shown the products, I would hope that you can look at that and say, yeah, that's going to happen because SN1 reactions, the cation can rearrange like that.